his work. And there are no questions. Questions are left to the discussion outside near to the posters. So I'll proceed to call all the names. I just have the last name here. So for me, everyone is either doctor or doctor to be. So I'll generalize to doctors. So Dr. Geschkenbein, first.
His talk on the last conference in Madrid. So with his nice squid, he can measure not only temperature but vortex position, and he did a great experiment where he pushed single vortices through the microbridge, and they were jumping from pinning center to pinning center under the direction of the force, and they observed some interesting broken spring effect, and it looked to us a bit as this game where one moves balls through a maze, and sometimes it comes to the hole and sometimes not. And from this analogy, we can actually learn quite a lot of the experiment, and you will see more at the poster.
Next speaker, Dr. Mockley. Oh, Dr. Kramer, I'm sorry.
Hi, my name is Anna. I'm a doctor to be. I'm a PhD student at Bina Kaliski's lab at Bar-Ilan University. We're a scanning squid lab, and the squid has the possibility to measure superfluid density with very high accuracy. I'm going to show in my poster 2 studies where this capability becomes extremely useful. One is the modulation of superconductivity on thin films grown on STO substrate, where we see the superconductivity modulate on the structural domains of the STO. The second study I'm going to show is what Bina talked about yesterday, which is the modulation in superconductivity in niobium titanium nitride films near the superconductor insulator transition. My poster is number 20. Hope to see you there. Thank you.
So the third is Dr. Mockley, vortices in the pair density wave phase of multilayer superconductors. I apologize for the previous speakers that I didn't say the title. Please.
Good evening. This is theory motivated by some experiments on artificial Kondo superlattices. These are very complicated, strongly correlated systems. But this theory has very, very simple ingredients, and they are the following. 3 identical superconducting layers. They are strongly Pauli limited by a perpendicular external magnetic field. Because of the symmetry of the system, the outer layers experience Rashba spin-orbit coupling, and the layers communicate. This extremely simple, apparently simple system displays, in my opinion, this amazing magnetic field temperature phase diagram. At low magnetic field, you just see what you would expect from a Pauli limited system. But at high magnetic fields, you see a new superconducting phase, which is robust against an external magnetic field, which is a pair density wave. It is a parity mixed superconducting phase, if you want, for instance, S plus P, and it is separated by a first order phase transition. So I want to know what happens if you consider orbital limiting on top of that. I can say that there is something very interesting happens to the vortex core sizes, which I will show you in more detail at poster number 3. Thank you.
Dr. Potra will tell us some new experimental insights into the surface superconducting state.
Okay, so here I will present in this poster some experimental results concerning the property of small cubic vortices in the superconducting state, the surface superconducting state. So we know that in this state there is short vortices, but less is known on the deepening of these vortices on the transport property. So specifically we have studied VI curve and also noise properties of these vortices when they are moving. And we see strong analogy and strong similarities with the Abrikosa vortices in the mixed state. Also, we have studied the case of, you know that normally surface superconductivity is expected when you have a magnetic field parallel to the large surface of the sample. In fact, experimentally, we see surface superconductivity even in the perpendicular geometry. So here we have demonstrated that this is due to small-scale surface roughness and that this surface superconductivity can be completely tuned by a proper surface treatment. So I will be happy to discuss with you of this result. Okay.
So next is Dr. Pinheiro. He will tell us about effects of thickness inhomogeneities on the flux of avalanches in superconducting films.
Good evening to everyone. My name is Lincoln. I work at Federal Institute of São Paulo, and I'm PhD student in the Federal University of São Paulo under Wilson Ortiz group. Well, in this poster, we will show you our first results in a systematic study of effects of thickness inhomogeneities in the flux avalanche in superconducting films. And our motivation is, in some cases, we cannot build device directly on flat surface. Sometimes, for example, as in radio frequency cavities for accelerators, we want to deposit superconducting films in a complex shape. So different gradient thickness and different thickness are around devices expected. And we want to study and to understand what would be the effect of this gradient thickness, not only in the smooth penetration, as we can see in the sequence of images on the top of the poster, but also in the avalanche regimes. So if you want to discuss more about this kind of subject, please come to my poster. Thank you.
So next speaker is Dr. Peña. She'll tell us about pseudogap manifestations in the kinetic energy density of bismuth, strontium, calcium, copper, oxygen single crystals.
Hello, my name is Paola. I am a postdoctoral fellow at Universidade Federal do Rio Grande do Sul in Porto Alegre. And this work is about the kinetic energy density in several single crystals of this system, the bismuth 2212. And we find that this kinetic energy density, which is a purely superconducting parameter, when this is plotted as a function of the Hall concentration, this shows this peak. And we observe the same behavior in the superfluid density, which we obtain from this type of measurements too. And we think that this is a manifestation of the pseudogap phase inside the superconducting phase. But actually, we think that this peak is because of the collapsing of the pseudogap phase. And this result would be consistent with the existence of Van Hoff singularity in the density of states, and with a quantum critical point at this value of p around 0.18. We are working in these results already. This is not a finished work, so we are open to discussions and new ideas. So that's because I am presenting a poster here. And I hope you remember me, because I don't remember the number of the poster, so I will be there, I will be around, so we speak there.
Next is Dr. Roma Guerra. He'll tell us about phase coexistence of superconductivity and magnetism driven by spinorial order parameter in heavy fermion compounds.
Hello to everyone. In more 2 layers, we are ending this section. So I try to be as simple as I can, since this is the most complicated slide of this section. Since Mauro spoke a few words about this interaction in his presentation, it will help to get the idea. The idea is to find a state where coexists the superconductivity and the magnetism. To make this model, I use the Landau formalism to make a proposal for the superconductivity functional, and also one for the magnetization. So it's very simple, the psi square and m square, plus the psi fourth and m fourth. To make it work, I need one interaction. So I introduce this one. This interaction make a coupling between magnetization and the wave function. Since this is a vector and this is a spinor, I need a special product. So I introduce the Pauli matrix. And to make use of the Pauli matrix, I need to write the order parameter as a spinor with 2 components. So the idea is to find the coexistence of magnetism and superconductivity that's sustained by the interaction. So what you will find out in the poster is those phase diagrams, that's temperature and pressure. It's not exactly pressure, it's the now temperature depends on the pressure. So essentially is the critical temperature of the magnetization against the temperature. So we cross the phase transition and we expect to find this coexistence. So this is the work. Thank you.
Dr. Rumi will tell us about first order vortex phase transition in bisco strontium, calcium, copper, oxygen with low doses of correlated disorder revisited.
Good evening, everyone. I have to clarify that I am also a doctor to be. More specifically, I am doing my PhD in the low temperature lab in Bariloche, where the 2001 edition of this conference took place, under the supervision of Dr. Janina Fasano. And I am here to tell you about a system that many of you who are present here studied about a decade ago. And if you look at the panorama presented in the literature of vortex matter in visco with low doses of columnar defects, there are still questions to be answered, and we employed the technique that Martin referred in his talk to as his classical technique, which is whole probe magnetic magnetometry. So I invite you to visit the poster number 23. Thanks a lot.
Dr. Vizarin, he'll tell us about dynamic phases induced by surface effects in type 2 superconducting stripes with triangular pinning arrays.
Good evening, everyone. My name is Nicolas Zari. I'm here to talk about the dynamic phases induced by surface effects in type 2 superconducting strips with your triangular pinning arrays. Okay, so this work isn't done, so we're suggesting suggestions and ideas for us. Okay, but the motivation is to characterize the vortex dynamic phase in a superconducting strip. We're especially interested in the surface effects on the dynamic phases. So we consider superconducting strip, okay, 2 widths, 0.5 lambda and 0.75 lambda, both with triangular pinning. In this case, we consider the 2 samples we're studying with the same parameters, or well, I can say the same applied magnetic field, which is 68 phi0 per lambda square, the same pinning density, same pinning size, and same pinning strength for both samples. We're just using the width as a variable. Okay. So the vortex motion is described using a set of Langevin equations, where we have the vortex-vortex interaction, the vortex interacting with the shielding screening of the surface, the vortex interaction with the current, and the vortex interaction with the pinning sites, and the vortex interaction with the self-images outside of the sample. So we obtain the vortex ground states using simulated annealing technique. We can see that vortices are pushed towards the center of the sample through the surface effects, and this induces different dynamic phases. We can see here in the velocity against transport force and also the derivative velocity against the transport force, the three phases when Lx is 0.5 lambda, and when the width is larger, 0.75 lambda, we have 6 dynamic phases. So we're assessing suggestion. We intend to do more calculus with different widths. And thank you. Come to my poster 18. Thank you.
So we thank all the speakers and close the session.